This is Math 251, and we're looking at section 13.3. We'll continue to do double integrals, but we'll look at doing them now in polar coordinates. We've already seen that a double integral has the form, the double integral of whatever function we're trying to integrate, dA, over some region R. R, again, is a region in the xy plane, and dA is either dx dy or dy dx, depending on the order that it's written or that we've been able to write it. We now ask this question: what if the region R is more easily described in polar coordinates? How does that affect F? And how does it affect dA? Changing the function f into its polar form is fairly straightforward. You may remember from using polar coordinates in the past, we certainly used them earlier this semester as well as in Calc 2, that you've got some equations to convert back and forth. Specifically, x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is equal to r squared. If you use these equations, you can usually convert your function f without too much trouble into polar coordinates. The differential dA is another story. That's going to take us a little bit more work to get to. We need to think about the geometry a bit. We certainly know that in rectangular coordinates, if we've got some region R, this rectangle here, what we always did was we partitioned our region into a whole bunch of little rectangles. Like so, right? And one of these little rectangles is our dA. That little rectangle, we could say, has length dx and width dy. And so dA was just dx times dy, or possibly dy times dx, it wouldn't matter, as far as the geometry was concerned. Now let's think about what's going on in polar coordinates. This, of course, is what we always call a rectangle. And the rectangle in rectangular coordinates has the property that x varies between two constant values, and y also varies between two constant values. X here goes from A to B, and y goes from C to D. Let's think about what would happen if we did something similar in polar coordinates. In polar coordinates, instead of x and y being our variables are r and theta. Just like x and y went between constants, I'm going to set r as between two constant values, a and b, and theta also between two constant values, alpha and beta, following the tradition of using Greek letters to describe angles. What does that look like? Well, if r is going from a to b, r equals a would be this smaller circle, just a piece of it's visible here. Notice that's got a radius of a. And r equals b is this outer circle. Again, just part of it is drawn. Notice that's got a radius of b. So the radius goes from the smaller one, r, to the larger one, b. Theta, going from alpha to beta, this dotted line or blue line here is theta equals alpha. And over here, we have theta equals beta. So you can kind of imagine sweeping out this region as the angle sweeps from alpha to beta. This region is actually called a polar rectangle. And if you're thinking that doesn't look much like a rectangle to me, I understand why. But the reason we call it that is because of the fact that the radius only goes between two constant values and the angle goes between two constant values, just like x and y did to form our standard rectangle. All right, what would a partition look like? Well, you remember that when we did the partition up here, we drew our lines parallel to the x-axis and then parallel to the y-axis because our variables were x and y. If I do something similar here, I'm going to start by drawing parallel to the radius lines. The radius are these curved arcs, or radii are these curved arcs. So my partition is going to draw a whole bunch of parallel curved arcs. What about theta? Well, let's see. If I increase my theta a little bit, I'm going to go from alpha to a little bit more than alpha. And then a little bit more than that. And a little more than that, and so on. My angles keep just getting bigger a little bit at a time. So that's what a partition of the polar rectangle would look like, where again we could pick out one little piece of this, and that would be our dA. On the next page, we're going to talk about how to calculate dA. Here's a partition that I drew on the computer, a little nicer than what I drew by hand. And again, I'm actually calling it delta A right now. We'll calculate delta A, and then we'll let all the pieces shrink infinitesimally small to make them into the differentials at the end of our process. So we're looking at this little polar rectangle. We're calling it delta A sub k. And within that little polar rectangle, we've chosen a point. We're going to imagine that that point, r sub k star, is exactly in the center of the section. This piece here is redrawn but enlarged over here. So once again, you can see this point right in the center of our polar rectangle, rk star, theta k star. The area of that piece is delta A sub k. Delta theta is the little increase in theta, and delta r is the little increase in r. Basically, our delta theta here was right there, and our delta r over here was right there. They're labeled here as well. My goal is to find the area of that shaded part, the delta AK. In order to do that, we need to remind ourselves of a formula from trigonometry for the area of a sector of a circle. The area of a sector is 1/2 r squared theta. What I'm going to do is I'm going to think of this shaded part as being the difference between the areas of two sectors. I have the large sector overall, and then I also have a small sector in here. And if I take the area of this large sector and subtract the area of the small sector, I'll be left with my delta AK. So let's write that much down. All right, so I'm going to get straightened up for you here. Okay, I gotta see if I can get everything in the window that I need. Here we go. The area of the large sector, using my sector formula, is 1/2 times. Now for the large sector, the radius here, for the large sector, is going to go all the way to RK, and then it's going to go 1/2 of delta R further, right? This is the RK line right here. And I've got 1/2 of that delta R that it has to go further out. So this is going to be RK star plus 1/2 delta r. And that's what I'm going to put in for this radius. That gets squared, and then times the angle, which is our delta theta. All right, what about the small radius? Let's label it up here. The small radius is right in here. And that's going to be the RK backed off by half of delta r. So RK star minus half of delta r. So plugging that into my formula, I have 1/2 RK star minus 1/2 delta r squared times delta theta. All right, that's everything from the geometry. At this point, we just have a whole bunch of algebra to do. So let's get started. I'm actually going to factor out the 1/2 delta theta because that's in both terms. And then I'm going to have the RK star plus 1/2 delta r, square that, minus, I factored that out, so RK star minus 1/2 delta r squared. Squaring this will give me RK star squared, and then the product is 1/2 RK star delta r, but I'll have two of those, one from the inners and one from the outers. So 2 times that half is just going to give me 1 RK star delta r plus 1/4 delta r squared. Now I'm going to subtract the square of this. Again, RK star squared minus, and the same deal, right? That'll be 1/2 delta r RK star, but we're going to double that because there's one from the inners and one from the outers. So we'll just end up getting a minus RK star delta r plus 1/4 delta r squared. All right, let's do a little mental algebra here. I'm subtracting these, so the RK star squareds will subtract off to 0, and so will the 1/2 delta r squareds. So I end up with an RK star delta r minus a negative, or plus another RK star delta r, meaning I now have 2 of them. And letting the 1/2 multiply with the 2, I end up with that RK star delta r delta theta. So that's the area, my delta A sub k. If I let all of my pieces become infinitesimally small, in the limit I could rewrite that as the differential dA. If everything's infinitesimally small, the RK star is just r. There's really only one point in my little area now. And the delta r becomes dr, and the delta theta becomes d theta. So there is the form for dA if I'm going to do my integral in polar coordinates. Let's write that out formally on the top of the next page. If I have the double integral over a region R of a polar function, f of r and theta, dA, in order to do that integral, I'm going to have to take this dA and always replace it with what we just calculated, r dr d theta. So this is our big difference between integrating in rectangular coordinates, where dA is dx dy or dy dx, and integrating in polar coordinates, where dA is r dr d theta. In the next video, we will do a few examples.